我们非常荣幸邀请到 Ross Mitchell 博士给我们讲今天晚上的一个 webinar。Ross Mitchell is a professor at the Institute of Geology and Geophysics at Chinese Academy of Sciences in Beijing. He holds a PhD in geology and geophysics from Yale University and was a postdoc fellow at Caltech. His research has been published in Nature and Nature Geoscience and covered by Science. So he's the author of the Next Supercontinent, so published last year by the University of Chicago Press, in which Mitchell uses Earth's distant past to predict its potential future. So tonight he will give us a webinar on the next supercontinental plate tectonics of the Earth of the future. So now let's welcome Ross Mitchell to have the seminar. So Ross, you can share your screen now.
OK， 看到吗
Yes, yeah.
OK， 开始吧
Yes, please.
OK， 谢谢你 very kind introduction. And 大家好，晚上好。Thank you everyone. 我知道今天是星期六。So thank you very much for coming and listening on a Saturday. The next supercontinent, plate tectonics of the future. So I recently wrote a popular science book. You see the cover on the right side. And today I want to talk about the science behind what is happening presently on the Earth and what may happen in the future. I first and foremost have to thank the innovation. Okay, I'm on the editorial board of the innovation, also on the editorial board of Innovation Geoscience. I regularly try to publish a few papers in the innovation, most recently this paper on mantle convection. And I want to highlight this paper because you're going to be hearing a lot about mantle convection. The Earth has a top layer, the crust, and a bottom layer, the core, but the middleman in between the hot core and the cold crust, we have the mantle, which is convecting like your oven at your home, where cold things sink and get replaced by hot things rising. And the mantle is the thickest layer of the planet, and I think one of the most important. So 我是美国人 okay, and 小孩子的时候 I lived in 法国 for a couple years. Before 中国 I worked 在澳大利亚 and 现在我在北京。所以 as a person, I have lived on North America, Europe, Australia, and now Eastern Eurasia. So the story you're going to hear today about the continents is really personal to me because, well, I probably work on this because I was very lucky as a student and as a child to be able to travel the world and look at the world map as a system. 在北京我有1、2、3、4、5、6个中文学生 6 students, and Earth is a complex system, okay? And my lab group, I think importantly, wants to have expertise in Earth as a whole. And if you want to do that, you really need to cover all areas. So my personal expertise from my PhD was in geophysics. So Liu Yushu is my expert in paleomagnetism, the magnetism of rocks, we'll talk about today. My postdoc, 最好的 here, Lu Kai, he is the geochemist, okay? And then I have 3 students for the 3 different rock types. We have Liu Xu, he studies igneous rocks. Okay, those are basalts and granites. We'll talk about those today. Ochichi Tashinaren, he studies metamorphic rocks. That's what happens when continents collide, which we'll obviously talk about today. And then sedimentary rocks. Chanfangfang studies, and this happens in all different geologic settings. And as we'll talk about today, very often when continents pull apart, but also when continents come together. And in today's modern science, I think many people listening today will probably have recently gotten involved in machine learning. So last, but definitely not least, we have Jiang Jilian, Sichuanren, and she is focusing on machine learning on really kind of all different aspects. So that's the Milao Shi group, and always looking for new students that are motivated. So please feel free to contact me. And Zaijianguo, also very happy. 今年浩年 very special year. 我结婚了. So thanks to my wife for her support. Okay. 开始吧. Everyone knows what a continent is. Okay. Today we have the 6 or 7 continents scattered around the globe. But if you rewind the tape, if you go back about 200 million years ago, wow, what do we have here? All the continents have come together. Now, let's look this forward in time. Today, we're going to be talking about supercontinent, okay? Everyone knows what continents are, but really, what are continents? What's the definition of a continent? Well, I would argue that continents are only rifted pieces of a supercontinent. You're looking at a supercontinent, and as you'll see, the continents find their meaning as they break away. So here, North America, break away, Canada, Mexico, okay, then Australia, India, break away, South America, break away, and then finally, Australia, break away. Okay. Now, if I'm talking about the future, what has happened in the past? What's happened in the past, and don't worry, we'll talk a lot about this just to give you advance notice. Earth, in its 4.5 billion year history, has had 3 supercontinents. So the continents come together, then they break apart. They come together, they break apart. We call this the supercontinent cycle. And the supercontinent cycle is very similar to Zaijianguo with the 4 kingdoms. If you are united for so long, you must break apart. If you break apart for so long, you must unite. So I really couldn't find a better metaphor for understanding the supercontinent cycle than the 4 kingdoms. Now, that's in space. What does Earth history in time look like? As I mentioned, Earth is 4.5 billion years old, okay? And today's story will really only be about the most recent 2 billion years, okay? Before 2 billion years ago, not only is it very hard to know what exactly looked like, maybe Earth didn't form this phenomenon of supercontinents. And, we can think about why. And a lot of it has to do with mantle convection. Supercontinents, so they're a modern invention. In the last 2 billion years, we've had 3 supercontinents: Pangaea, Rodinia, Columbia. And so there appears to be about a 600 million year cycle. And if we have 1、2、3，为什么不4个人? Why not have a 4th supercontinent in the future? And that's where we'll finish today's talk, using the past to learn about what could happen in the future. And I should mention, 这本书我写的书, okay? This is my book, and my book very similarly it's been written in a kind of technical but still popular scientific approach. So hopefully, geologists would find it interesting, but hopefully scientists of all types, chemists, physicists, biologists, hopefully there's enough fundamental science in here that even if you're not a geologist, you can still find it interesting. And the book, similar to today's talk, goes from the most recent, Pangaea, to the more ancient, Rodinia and Columbia. The old, it goes farther back in time, and then learning the lessons from the past, then looks ahead to the future. And 在渐动你可以买的。OK， 开始吧。If we know anything about supercontinents, it's because we know a lot about Pangaea. Pangaea was the last most recent supercontinent, okay? Here's, I'll be showing the picture, beautiful artwork, again, in my Xiedishu. So you see a map on top of what Pangaea looked like, and on the bottom, a depiction of what Earth looked like at that time. So Pangaea existed about 320 to 180 million years ago. This is the time before which life was only in the sea. And this is the first time when life climbed up on land to give us things like trees and us, mammals. The atmosphere at this time rose to its highest level of oxygen. Today, we have Arsha Ardu, 22%. Believe it or not, during Pangaea, we actually had 大概30度, okay? Now, the most important thing for children especially is that Pangaea was the home to the dinosaurs. Pangaea, the story of Pangaea starts with a Dogwaran, 他叫 Alfred Wegener. And believe it or not, this is a Wegener figure, 他写的书, and this is Yao Jiao Yao R, okay? This is 100 years, over 100 years ago. He's drawn a picture that you will see today is very similar to our modern understanding of Pangaea. Pan means all, Gaea means earth from Greek. So he introduced the idea of a supercontinent. And how did he do it? Well, he looked at all the different continents, and this is actually something you can do with your child on a nice weekend day. You can cut out the different pieces of the continents, and you see on these continents, there's different lines of evidence. And all Wegener did was put the coastlines together and had the different lines of evidence line up. Those lines of evidence were fossils, climate-sensitive sedimentary rocks, things like limestones that form at low latitudes due to carbonate precipitation. And when continents break apart, things like basalts, hot magma, that's evidence of continents breaking apart. Therefore, they had to be next to each other. And of course, the coastline shapes. Everyone, 大家知道, Africa, western coastline, and South America, east coastline, they fit together almost perfectly. Now, Wegener focused on the continents, okay? But it took many, many, many years, even decades, before geologists developed the concept of plate tectonics. And really what was missing was data from the oceans. So testing Wegener's ideas, mainly about the continents, had to wait for data about the oceans, and you have to map the seafloor. So after World War II, with all these submarines and boats and magnetometers, we put that to use. Zaimegwo, 3 institutes, very important, Lamont in Niue, Woods Hole near Boston, and Scripps in California. And one of the ladies, Mary Tharp, she was a Nuren, she was a lady, and there was a bad superstition that ladies were not allowed to go to on the ship. So she had to stay back at the lab. But because of this, she was actually the cartographer. She was the one that made these beautiful maps of the data that was gathered from the seafloor. And before we had data, most geologists probably would guess that the seafloor was flat and featureless, no features. That was completely wrong. In fact, as you can see from Mary Tharp's beautiful drawing and map here, is there was high and rough topography known as the Mid-Atlantic Ridge. This is between Meguo and Europe, okay? And she discovered that there were mountains in the sea as well. Now, what was happening? That had to wait a few more years until after we had the maps. Then we started mapping the seafloor with magnetism. What they found was the magnetism of, originally they were using these lines of magnetism, very, very long lines of magnetism. And those were very useful during the war for navigating. After the war, we tried to figure out, oh, let's do some science. Why are these lines? And they learned that actually, as you go away from one of these lines, the magnetic field, the magnetic signature in this rock actually would reverse. And then it would reverse again, and reverse again, and reverse again, and again and again. So the magnetic dipoles were pointing up, then pointing down, then pointing up, and pointing down. Today we know this is because of a phenomenon called seafloor spreading. As the hot magma from the mantle upwells, it acquires the present-day magnetic field, and then it pushes, that new magma pushes that old crust away, and then goes and goes, and Earth's magnetic field reverses, recording this kind of barcode-like shape. So these are known as isochrons, iso meaning same, and chron meaning age. So along one of these lines, the seafloor is the same age. And so that was having to do with plates pushing apart. The next evidence in the plate tectonic revolution came from subduction, okay? Seismology is the line of geophysics that investigates earthquakes, okay? Every time an earthquake occurs, the sound waves that travel through the Earth's layers actually give us very detailed information about the internal structure of the planet. And this guy, Benioff at Caltech, even before we knew about what are come to be known as subduction zones, he identified these Benioff zones, where going deeper and deeper and deeper, earthquakes seem to occur along this sloping line. Well, it just so happens he had discovered what we now know is a subduction zone, where one plate actually gets pushed underneath another, along which earthquakes occur. So now we have seafloor spreading for moving continents apart, and we have subduction for moving continents together. Then Janadaren, Tuzo Wilson created this idea of a life cycle of a seafloor. Okay, and the first thing you have Diiga, continental rifting, continents break apart. The Arga, you have the seafloor spreading. The Sanga, you have a large ocean basin. The Suga, you have somehow subduction initiates. And the Wuga, eventually, now that there's subduction, the continents will collide, and the cycle has continued. So finally, Wegener maybe says, yes, the plate tectonics finally provided a mechanism for continental mobility. So this is the Goran, Wegener, he knew the continents had to put the continents separated, to put them together, the continents had to move, but he just didn't know how. Now we know that's because of plate tectonics. And this is the picture of the Earth today, broken up into all these different plates. And here is a beautiful map of the seafloor, where all of the different colors are different ages of the seafloor. And okay, here's a modern reconstruction of Pangaea. And as you will see, it looks very, very similar to Wegener's original Pangaea. And I should mention the records from the continents and the seafloors are consistent with each other. Now, when I was a student, 在大学, I read a very important paper. And scientists don't often identify problems, right? We always solve problems. So I give credit to these professors for writing a paper that didn't solve a problem, it pointed out a problem. They said there was a Pangaea problem. The current theory that old ocean crust being denser would close. And they noticed there was a problem. In fact, the young, less dense ocean crust closed to form Pangaea. 为什么? We will return to this later. So now that we know Earth had a supercontinent, what about Pangaea? What about farther back in time? Well, before Pangaea, there was a second supercontinent, and that was called Rodinia. Rodinia occurred about 1 billion to 800 million years ago. And unfortunately, there is no ocean crust preserved of this age. So reconstructing Rodinia has to rely on other methods. And importantly, on the Earth at this time, the first algae and multicellular life, known as metazoa, evolved for the first time. And that's what would become large animals like us. There's really 两个人 who were if Alfred Wegener was the father of Pangaea, really Paul Hoffman and Li Jianxiang, 想当然在青岛 and also Adelia, really they reconstructed Rodinia. So Rodinia comes from Russian, meaning motherland and birthplace, having to do with the evolution of life. And it started with the idea that Pangaea wasn't alone. We had a second supercontinent maybe before it. Now, like Wegener using the macroscopic big fossils, we didn't have those for Rodinia yet, so we can't use that for reconstruction. And as I mentioned, no seafloors. So evidence from Rodinia must be found with different data. And first Rodinia started with Paul Hoffman realizing maybe these mountain belts, known as geologists as origins, maybe they could be the key. And he noticed that Canada Meguo, known as a continent Laurentia, had a huge mountain belt known as the Grenville Mountain about 1 billion years ago. And so then he just looked at the other continents that had mountain belts around 1 billion years ago, and very much like Wegener, put the pieces, the coastlines together, matching this large 1 billion year old origin. And I should also mention a very important part about Rodinia is climatically a very intense climate event known as Snowball Earth, also discovered by Paul Hoffman. The idea that the whole Earth could become engulfed, covered in ice. This did happen, and it happened twice during Rodinia. So something about Rodinia was special to cause the Earth to become so cold. But I could give a whole nother talk about Snowball Earth. And here's Zhao Piar, Adelia, me and Paul Hoffman studying the Snowball Earth rocks. Then, so after Hoffman's first work, then Li Jianxiang come along, and he really brought Rodinia into a multi-dimensional space in terms of testing whether it really, did it really exist like Pangaea? And there's many different lines of evidence that Li Jianxiang used, but the one at the bottom, paleomagnetism, is really one of the most important at this age. And just very quickly, unfortunately, not too much time to talk about it, but the basics of Earth's magnetic field has a magnetic field, very strong. So if you sample a rock, okay, those magnetic minerals in that rock will be pointing to the North Pole. And if they typically will not point to the present day North Pole because the continent has moved due to plate tectonics. So the latitude of the paleolatitude is directly the paleomagnetism gives us the latitude, okay? But then the magnetic field is the same at every longitude. So how do you know latitude? How do you know longitude? Well, you get what we call multiple paleomagnetic poles, and you get a path. And as you can see in the picture on the right, if 3 continents, A, B, C, have these polar wander paths, the time when the supercontinent existed is when those paths come together, and the time when the supercontinent breaks apart, the paths diverge. So we can solve the longitude problem by having multiple paleomagnetic poles known as a path. Now, Janda Hando Rodinia. There's still a lot of controversy about how exactly Rodinia looked. I would probably argue that F is probably the most accurate. It has a very similar picture to the early Hoffman and early Li Jianshan maps, but some continents like southern Zhangguo Nanfang, okay, is not part of Rodinia maybe. Okay, so in order to have a cycle, okay, of supercontinents, we need at least 3. And the third supercontinent, Columbia, gives us that. From about 1.7 to 1.3 billion years ago, if you want a supercontinent cycle, we need at least 3 supercontinents. And as far as we can tell, it was Earth's first supercontinent. Again, Hoffman was involved. He focused on Janada and Meiguo, okay, looking at all, again, the origins, the mountain belts of this continent. But then really, it was Zhao Guchong, Zai Xianggang and Hong Kong, who really came along and did what Paul Hoffman did for Rodinia on a global scale. Zhao Guchong did that for origins and mountain belts on a global scale for Columbia. And then after that, we have Zai Beijing, CUGB, we have Zhang Shihong, Hao Pangyou, and he and others contributed to forming these paleomagnetic wander paths that allows us not only to have the origins, the mountain belts, but also have the magnetic data that allow us to reconstruct the supercontinent. So, wow, we have 3 supercontinents in the past. And if we have 1, 2, 3, 为什么不 we don't have a future supercontinent? And the interesting thing about Jintian today is that we are in between supercontinents. We have evidence of Pangea breaking up in Africa, okay? You have the Africa Rift. That's still ongoing breakup. But we also have evidence of the next cycle beginning. Think of India colliding with Asia to create Tibet Plateau in the Himalayan mountains. So the modern day is a very interesting time that is in between supercontinent cycles. So now let's look to the future with the lessons we learned from the past and ask ourselves, what about the next supercontinent? What might it look like? So before I got involved in this field as a student, the question that was being asked, which oceans close? And that makes sense. In order to form a supercontinent, in order to have continents collide, oceans must close. So again, there were kind of end-member theories. Some people thought that the Atlantic would close, that would create, something like that. And the other people say the Pacific would close. So let's talk one by one. Introversion, taking from people's personalities, the idea that you close the Atlantic back up. So the Atlantic was the ocean that opened up to break up Pangea. And it's kind of like Jigger and Jelly, playing the accordion. Pangea break up, Pangea close back up. So introversion, they would argue that you close the interior Atlantic type ocean, the ocean interior to the continents. Then extroversion came along and said the opposite. They said, no, Atlantic's not going to open. It's going to continue. And actually, it's the exterior ocean. And the problem with introversion is the Atlantic has really limited evidence of subduction. So if you want the Atlantic to close, you need subduction zones, and there just really isn't any evidence that there are large subduction zones forming in the Atlantic. Now, the extroversion theory doesn't have that problem. It has a lot handor subduction in the Pacific. In fact, many of you might have heard of the Pacific Ring of Fire. So all along the edge of the Pacific, we have these subduction zones. However, whether that means it will close, yet to be determined. Because if you look at it, there's no continent that's actually going across the Pacific Handa, okay? There's been hundreds of millions of years now, and the Pacific is still open. So maybe there's problems. So which oceans close? Okay, to form a supercontinent, oceans must close. But is this the right question to be asking? When I was a student, PhD at Yale, I was asked my qualifying exam to draw the tectonic force diagram, where you have the force of subduction slab pulling down, you have the seafloor spreading ridge push, you have the trench suction, you have the mantle below with the drag force, okay? Yeah, they make you draw all these different forces. And okay, but the question is, are all these forces created equal? And possibly more important, is there a spatial pattern when you think globally? This picture is simply a small localized drawing. It doesn't depict the globe. And I want to come back to my innovation paper and the idea of the mantle. So this tectonic force diagram focuses on the surface with a little mantle below, but that's not what Earth looks like. Earth has a massive mantle, and this mantle has these big convective shells. And I would argue that the mantle is an overlooked feature in the previous theories on supercontinent cycles. So here's my recent Nature Reviews paper, and there's two data sets, okay? By now, you will recognize the supercontinent Pangaea. That's Pangaea 200 million years ago. The colors, that's actually the mantle from seismology today. And you see the Hongsode? Well, there's this big blob, this big red blob sitting in the lower mantle. That's the shape of Pangaea. So there is a direct connection between the shape of the supercontinent at the surface and the mantle at the base of the mantle, okay? There is a direct coupling between the formation of the supercontinents and mantle convection. Now, we think about the Earth today, and you think, oh, we got all these continents, one here, one there, and they're all scattered. Boo, boo, boo. They are scattered, but very, very systematically. If you simply measure the angle from Africa at the center, Africa, the center of Pangaea, the last supercontinent, if you measure the distance from Africa to all of the other continents, on average, they are almost exactly 90 degrees, which means all the continents have gone 90 degrees away from Africa since the breakup of Pangaea. 为什么? Why didn't they go farther? Why didn't they go shorter? Why 90 degrees? Now, everyone looks at the Earth in the map like this with the equator on the center. But what if we look at the Earth today, but simply a different projection? Instead, we're going to have two equators, an equator up here, equator down there. But in this projection, we put Africa off to the side and the Pacific off to the other side. And you'll notice all the continents are in a straight line of continents. If you try looking at Earth in a different projection, you can see that the continents are distributed orthogonally. That is 90 degrees away from the center of the last supercontinent. So they've gotten as far away from Africa as possible, but they also haven't gotten any closer to Pacific. They are caught in between Africa and the Pacific. 为什么？有红色的 under Africa, and the other side, we have another 红色的, hot and hot. So what does that mean? These Hong Suda regions in the lower mantle, it's where the mantle's elevated temperature, okay? And although it may be a little complicated to think of, there's mantle upwelling, hot convection upwelling in underneath Africa, underneath the Pacific. And therefore, if there's two upwellings, in the middle, you have to have downwelling. What comes up must come down, okay? And so why does that matter for the continents? Well, the continents, they want to drift downhill, okay? The mantle upwelling causes kind of an elevated topography on a very long wavelength, on very long scales. And the continents, they broke away from Africa because they were going downhill, but then they get to this ring of downwelling where the mantle is downwelling between the upwellings of Africa and the Pacific, and the continents are happy there. They want to stay there. They like it there because it's like in the bathtub with your children, okay? At the end of the bathtub, you take out the drain and the water starts downwelling. And what happens to the rubber ducky? The rubber ducky moves right over the drain. Now, in this thing, the drain is downwelling, but on Earth, the convection in the mantle is downwelling. And the continents have drifted to be over this downwelling in between the two upwellings under Africa and the Pacific. So in my Nature paper, Zayelo Dashwe, we had the original theories of introversion A, extroversion B, and we said those two are wrong, okay? For introversion to happen, the continents would have to go back uphill on top of the Africa upwelling. They don't want to do that. For extroversion to be right, the continents would have to continue over the Pacific uphill upwelling. They don't want to do that. The continents are all comfortably in this ring of downwelling. So that's where the future continent collisions are going to happen. And that's where they've already occurred. As you can see, India slamming into Eurasia 20 million years ago, the most recent collision was right along this downwelling in between the two upwellings. So I honestly, came up with this idea from reading my advisor's paper. He had this theory. He presented a model where a new supercontinent forms 90 degrees away from its predecessor before it. He simply didn't think that it could be tested, and I realized we could use the paleomagnetic data to test it. Specifics I can't get into now, but basically that's what we found, okay? So here's our picture of Pangaea, okay? And in addition to the continents now, I want you to look at the colors. So the Huangsede, that's the upwelling, okay? And the Lansede, that's the downwelling. And if we go, maybe forward in time, okay? So here's Pangaea forming. This is time up on the top left. That's 200 million years ago, okay? So Pangaea forms and it develops because the continents, subduction brings the continents together. The continents collide, subduction has to move to the edge, and what goes down must come up. So we develop this upwelling beneath supercontinent Pangaea. That's why there's this Huangsede. And let's just watch as Pangaea breaks up. Let's watch the continents move away from the Huangsede and towards the Lansede. They're drifting downhill away from the upwelling towards the downwelling. And there's India moving right along the Lansede, moving right along the downwelling. And who's next? Well, Australia. So Australia currently is the fastest moving continent. And is it going towards Africa? No. Is it going towards the Pacific? No. Zomian, Yomian, yeah. It's going straight. It's going straight along the Lansede. It's following the subduction girdle to the north. So instead of the Atlantic closing, instead of the Pacific closing, our theory, orthoversion, this 90-degree away from Pangaea, predicts Amasia. We predict all of the other oceans, the orthogonal ocean basins will close. If you close the Arctic Ocean to the north, Americas and Asia will collide. If you close the Caribbean Sea in between Mexico and the south, you have the Americas collide. If you close either the Scotia Sea south of South America or the Tasman Sea south of Australia, you have Antarctica either go west towards the Americas or Antarctica go east towards Australia. But either way, it's along this ring of fire. So instead of talking about the oceans as the theory, we've actually used the dynamics of mantle convection to predict the kinematics, or who moves, predict which oceans close. So here's just a video of the continents where they are today, and you can watch our prediction for where they're heading to in the future based on our theory of not introversion, not extroversion, but orthoversion. And here we've chosen for Antarctica to go to the west, but it could also go to the east. So with this supercontinent forming at the North Pole, what would it look like? Here's a view from the North Pole of Amasia, the Americas and Asia colliding probably about 150 million years from now. So thank you, everyone, for listening. I would love to have talked in more detail. So if you have any questions on anything, whether about the theory or just anything about geology or plate tectonics in general, I'd be happy to answer those. And one thing, a nice thing about the book is I think it's about scientists as well as science, because ultimately science is done by scientists. And so there's personal stories in addition to the science, stories about why I became inspired by geology. And there's even a story about losing part of my right thumb, Zai Odelia here, Arling Liu, Zai Odelia, where a whole rock in front of me broke off. And we were many hours away from the hospital. So in the book I write, I lost half my right thumb for Rodinia. So if you want to hear more about the personal stories, if you want to hear more about the theories or the scientists behind the theories, please consider checking out 我写的书. So 谢谢大家, and I'd be very happy to answer any questions.
OK，谢谢 Ross，谢谢非常精彩的演讲。So while waiting for the questions from different channels, so I may have one or two very simple questions, okay? Because I'm not a geology background, so I may have very or maybe silly questions, okay? So first of all, so how the transitions of the Earth or the supercontinents may impact our daily life?
So already we know that earthquakes
Yes.
are probably earthquakes and volcanoes, okay,
Mm,
are two of the most violent forces on Earth, and they are directly consequences of the story I tell today. So you think about the massive volcano eruption out in
mm,
Tonga in the
mm,
Pacific Ocean recently. This eruption that can be seen from space.
mm,
Well, that's actually related to a subduction zone to the north of Audelia. And why? Because Audelia is the fastest moving continent heading towards
mm,
Eurasia. So you get rapid subduction there. It's the fastest subduction on the Earth is causing the earthquakes. And then that rapid subduction melts the water goes out of the rock, and that water releases these magmas in the form of volcanoes. So if you think about like the earthquake in Fukushima and Ruben that caused big problems for the nuclear power plants, why is that happening there, Zairuben? It's because it's right on this ring of fire
mm,
where we're going to predict the future supercontinent to form along. So I really try to emphasize, even though we are talking 100 million years in the future,
mm,
it takes many earthquakes and many volcanoes to get there. So even in our lifetime, you will probably live through many events such as these. Even though these are slow tectonic processes,
mm.
they cause short-term phenomenon like earthquakes and volcanoes.
Okay. Yeah. 谢谢.
没事。
So let me check whether or not we have questions. Okay, from the audience. So far we do not have. So while we keep waiting, so I may have another questions. Okay, so
OK，
let's
行，
leave
没有问
from
题。
the physics and the engineering perspective. Okay,
Great.
so with the knowledge of the supercontinent and the plate tectonics. Okay, so is there any way that our human beings can do anything to get intervention with this process? Is it possible or not? Or because the Earth is so huge, that's the nature, we can do nothing apart from understanding.
Oh, that's an excellent question.
Mm,
So actually, the year that I published my Nature paper, I got a
mm,
call from a studio in Hollywood, and they said, "Hey, is there anything humans could do to actually accelerate this process and
yes.
make it happen?"
Mm,
Maybe, probably not, but
mm,
actually, things like nuclear weapons, if you actually, detonated them near one of these hot spots where the mantle is upwelling. Maybe you could superheat the mantle, which actually could accelerate plate tectonics. But most importantly, humans are a geological force. So
mm,
even if we couldn't cause a supercontinent to form uh, next week, in terms of things like controlling the climate, and I try to cover this in the book a lot, there are lessons we can learn from geology. Volcanoes are a great way to actually
mm,
cool the planet. The
mm,
the particles that get up in the stratosphere atmosphere actually reduce the reflectivity of the Earth. So we get a 1 degree or so cooling. So one of the theories on how to solve global warming is actually mimicking and behaving like a volcano and
mm,
injecting into the upper atmosphere some of these aerosols. So actually, I think there's a lot of lessons that can be learned from the natural experiments run by the Earth over millions of years that can actually be applicable in terms of decades indefinitely, our children's children and, hundreds of years. In a country like Zhangguo, where you have
mm.
5,000 year history, there's a lot we can do on that time scale.
Okay, so thanks a lot again. So while waiting for the new questions coming, so 我们一起来看一下，现在有个插播一个，所以我们这个是在 promote 我们这以科技通行这样的一个 webinar，所以我们助力创新，让科学尽量变得更加 easy。我们的 innovation 微信公众号 尝试将艰深晦涩的专业术语科普化，为您解读每一篇文章，和你一起理解科技创新的最新进展和突破。那么，我们可以扫码我们右边的这样的一个二维码，一起来关注我们这样的一个公众号，好吧？我们后面还有一页信息。那么这边是进一步的公众号，然后有视频号以及我们的学术交流群。如果你对今天的 webinar 或者是以前或者将来的这样的一个我们每周六的这样的一个讲座感兴趣的话，都可以通过扫码来加入我们，跟我们一起来讨论。好的，那我们继续来看一下我们的问题。我们好像有一个问题是来自于别的平台，So Ross, we have a
嗯
question from the other channel, so I may read for you, okay?
嗯
So by next supercontinent, the sun will be much brighter than now, so the albedo and the habitability of the Earth will be redefined. So could you predict what would be the climate be?
嗯，伟克，谢谢，好问题。So yes, the sun is getting brighter. That's solar luminosity. But that's very long time scale. Some people have recently published a paper using climate modeling to actually they take our reconstructions of the future and they run the climate models we do today. They run it with the different continental configuration. And not my work, but what they found is that the next supercontinent is going to be a very, very bad place to live, and very hot. So all the volcano, you form this big continent, and then you have this big ring of volcanoes around it. It's a lot of CO2 emissions. And actually, you can take a lesson from the last supercontinent, Pangea, the largest mass extinction ever to occur on Earth occurred during the time of Pangea. So even though oxygen was very high, actually getting all the continents together for multiple reasons can actually be very challenging in terms of the type of climate and environment, and even competition between different sorts of species. If you used to live on separate continents, but now those continents are side by side, now actually we kind of start war, ecological war. So for multiple reasons, supercontinents are an ecological, environmental stress on life. But humans are very inventive, and we got a lot of time before them.
Okay, good. So in your seminar, so you describe the possible pathway for a new supercontinent. Okay, so there's one question from the audience is, so are there any math equations or math models to predict this path?
That's why, if you just take, we know very precisely with GPS satellite where the continents are moving right now, but things can change. Okay.
Yeah, sure.
All of a sudden, a continent can take a right turn. We know this with the chain of islands out in Hawaii. They go straight, and then 50 million years ago, they start going north. So you can't just press fast forward and forward. That's really what inspired me to kind of see if there was a geometric pattern going from one supercontinent to the next. And the dominance of this degree 2 mantle convection, the fact that we don't just have one upwelling, but two upwellings, to me, that provides a pattern, a geometric pattern that should allow us to do such a model. And honestly, that's a great question, because that is exactly the frontier research that we're working on now.
Okay, good. So yeah, we have one last question for a moment. So are there geological changes related to the magnetic field? So when you have the geomagnetic field changes, so are we able to expect there's some geological changes as well?
Yeah. So Earth, we have a very strong magnetic field. We tend to, it's great for navigation, but it's also great for life. Okay, the sun has all these cosmic rays, and these cosmic rays are very, very bad to your DNA. Okay, so this magnetic field is very essential for sheltering us, shielding us from those cosmic rays. So there is some theories out there that when the magnetic field reverses, it does so by weakening and then regrowing in the opposite direction. And it needs to be tested further, but it's very possible that during those transitions, you actually have times of species turnover. Um, and but the magnetic field never really goes to zero. So actually, if there are more cosmic rays coming in, they might not kill you. They might just cause mutations in your DNA. And mutations are not always a bad thing, right? Sometimes they can get selected for. And there's periods of time where there's no reversal of the magnetic field. It's just constant. And times like today were quite frequently. And this probably controlled by mantle convection and the supercontinent cycle. So I'm very impressed with the questions because that's another frontier. Okay, I've taken the supercontinent cycle down to the mantle level, but the magnetic field is generated in the core. So, one step further in this theory is using the magnetic field as a further constraint.
Okay, so great. Thank you very much for all the good lectures and also very good answers for the questions. Okay, so as we have no more questions from the audience, I believe we can end today's webinar here. So let's thank Dr. Ross Mitchell again for the great talk tonight. Okay, so it's so nice to have a great night to learn new things. Okay，
谢谢你。
OK， 谢谢。那我们今天的今天晚上直播就到这里，好，谢谢，拜拜，
拜拜。